Well, good afternoon, everybody, and welcome to today's webinar on the Mauve Science Program, and thank you all for joining us. My name is Richard Archer. I'm part of the Blue Sky Space Team. I'm based in our London office, and I'll be hosting today's session, which is expected to last approximately 60 minutes. This is actually the first in a series of Mauve webinars we are planning for 2026, and each one will discuss different aspects of the Mauve Science Program, which is a UV mission to study stars. Today's webinar will focus firstly on introducing Mauve and Blue Sky Space, but primarily on introducing the science program, the science goals, and the opportunities for the first year of the multi-year program. I'm delighted that we're joined by members of the Mauve Science Team who are going to present three of the science themes, the diverse science themes that they're personally involved in. Dr. Emma Whelan is an associate professor in the Department of Physics at Maynooth University in Ireland, and her research focuses on star and planet formation. Emma's going to be giving a talk on her use of Mauve for studying Herbig stars. Anusha Ravikumar is a PhD scholar at Western University in Ontario in Canada, and her research focuses on hot, rapidly rotating stars and their circumstellar environments. And Anusha is going to be giving a talk on a population study of classical BE stars. And finally, Dr. Alejandro Nunez is a researcher at the University of Columbia in New York, and his research focuses on understanding the magnetic activity in main sequence low mass stars. I'm also going to be helped by two of my colleagues. Dr. Marcel Tasseni is the co-founder, or one of the co-founders of Blue Sky Space, and Benjamin Wilcock is a senior program manager and runs the 3-year science program for all of our members. So the agenda, Marcel's going to talk briefly about Blue Sky Space and our ambition as an organization. He'll then hand over to myself. I'll introduce Mauve and the satellites and its capabilities. I will then hand over to Ben, and he will talk about the science program and the scientific goals for Mauve. We will then hand over to our guest speakers. We will have 3 science-themed talks from Emma, Anusha, and Alejandro. They'll last about 10 minutes each. So that will roughly be 8 minutes with 2 minutes of questions. I will then briefly talk about Year 2 science planning, and then we will open up the floor for any final questions and answers. We are today using the Zoom webinar platform, so it may be a little different for some people joining, but try and post any questions in the Q&A box on Zoom. It's not marked chat, it's marked Q&A, and my colleague Parul will be moderating all the questions, and we'll stop at regular intervals to answer questions. I will be recording, or we are recording today's webinar, and I will plan to send that out in the coming days. Okay, on that note, I'm going to hand over to Marcel, who's going to talk about Blue Sky Space.
Thank you, Richard, and thank you all for participating in today's call. So a little bit of background on Blue Sky Space. Richard mentioned there's multiple co-founders involved in setting up this organization. We started this from an academic background, and we did this in the context of a desire to augment the number of datasets that are made available for space science, from satellites obviously. And we're doing this in the context, of course, of a rapidly evolving landscape with a number of satellites being proposed, but some of them taking quite a long time to be implemented. And so in that context, we are focusing on delivering datasets for space science from a number of satellites that are primarily located in a low Earth orbit environment. We're looking at fairly small, simple satellites. We are not competing with the very large flagship missions built by the big space agencies. On the contrary, we're looking at working in synergy with many of these facilities. And the way we select our satellites, and I'll talk about this next slide, is really focusing on areas in which there is demand from a science perspective from a wide community internationally. So Mauve, that you can see on the bottom left here on this diagram, is really the start of the journey of a series of satellites addressing a number of different science cases. You might have heard about the larger Twinkle space mission, which is focusing on doing exoplanet atmosphere spectroscopy from the visible to the infrared. And then there's a number of other satellites that we're working on as well in preparation. So Mauve Plus, a larger class of UV instrumentation for a few years further down the line. And then the last project, which is perhaps the most ambitious at this stage, is Radio Luna, which is a contract that we've got with the Italian Space Agency to design a fleet of satellites orbiting around the moon to do radio astronomy. So the methodology that we've got for these satellites is to work with industry experts internationally. And so we pick platform providers and instrument providers who are most suited for specific tasks and specific science cases. The overall philosophy throughout these satellites is to work with the suppliers to pick existing technologies which have been either flown before or are analogous enough for implementation into a low Earth orbit environment. So we pick technologies which have high heritage, and that allows us to keep the costs and timescales very much constrained. And the desire with these different satellites is to deliver them in 3 years or less. To do this, we've assembled a team to work on all the different aspects which are necessary to be able to deliver scientific data sets. So whether it is in software development, science operations, spacecraft engineering, payload instrumentation, and so on, we've put together a team to deliver this. And as we scale the organization to work on the subsequent satellites, we will also be increasing the team size. And we're always on the lookout for experienced and enthusiastic staff members to join us. Now, Blue Sky Space is operating in a different model than maybe many of the facilities historically have been. And so the way we do this as a private company is to take the risk upfront in financing these satellites. And we do this through a combination of sources which are listed here. It's a combination of participations from the institutions who buy into the membership program to get access to the survey programs, plus support from grant-giving organizations. So in the context of the various satellites we've been working on, we've secured funding from a range of UK and European grant sources. In fact, the European Commission has partly funded the Mauve satellite. And then the third component is private investment from organizations and individuals who want to see an increase in scientific activity and space capabilities internationally. And so the way we operate this is that the subscriptions that we offer to the universities who participate in the science programs help fund the operations and the running of these satellites, but also do the preparation work and the scaling up for the subsequent satellites. That allows the company to grow in an organic and sustainable way and hopefully increase the number of scientific opportunities that we address and deliver satellites for in the coming years. So I think with that, I'll pass over to Richard to introduce Mauve.
Thanks, Marcel. So what is Mauve? So Mauve is a UV visible spectrophotometry satellite, and we're delivering this mission as a 3-year collaborative program, which will primarily study stars. I guess one point to note here is Blue Sky Space do not decide the science. It's the members that join the program who form a science team, strategize, collaborate together, and they design the individual science cases and ultimately the observational program. So far in the first year of the science program for Mauve, we've allocated 5,000 hours, and those have been allocated over 4 broad science areas, and Ben's going to talk about them in a few slides' time. And really that lends itself nicely to doing one of two things, either long baseline observations, so you can sit and stare at a target for long periods of time, particularly good for things like flaring stars, or large-scale population studies, so doing snapshots of lots of targets. And of course, what cuts through all of these is the ability to revisit these targets during the entire 3-year lifetime of the program. So seeing how they've changed, the variability aspect. So it's a strong time domain opportunity for science. The satellite's been built by C3S in Hungary. They're also operating the satellite for us. They're doing the mission operations and control. And also ISIS Space, who are doing the ADCS system, for Mauve 2. And we're really grateful that the European Commission has part funded the one second. Let me. There's my video back on. As part funded this project, in a certain aspect, they part funded the construction of Mauve. So a deeper dive into the satellite. There's a CAD drawing of Mauve on the left. So I'll walk you through this. So at the front, we have the telescope here, which is a telescope provided by an organization called Medialario in Italy. It's a 13-centimeter telescope. So Mauve is very much optimized for the study of bright targets, and that's connected to two spectrometers, which are in the back of the satellite, and they're connected by two fiber optics. So we have a redundant spectrometer. The spectrometer is 200 to 700 nanometers, so that's near UV and visible. It's provided by a company called Avantes in the Netherlands. It has a resolving power of between 20 to 65, so relatively low resolution, and it uses a Hamamatsu CMOS linear array detector. Mauve isn't looking at patches of sky. It's very much single target spectroscopy. So we try to isolate a target within the telescope and the fiber and observe it. And so the field of view of Mauve is 95 arc seconds full cone. So what can you see with Mauve? So this is Mauve's field of regard. Actually, it's a 1-year coverage map. The field of regard goes from 30 degrees to minus 45 degrees declination. It covers the entire ecliptic plane and parts of the galactic plane, including the galactic center. And I guess in this slide, the most important thing to note is the colors, because the colors denote the coverage you will get on a target in a 1-year period. So if any of the targets are in these purple areas, you will get no coverage. And as you move from green through to yellow, there are increasing coverage on those targets. So I'll give you an example. If your target, for example, Epsilon Eridani, is located here, it's in the yellow zone. We call it the golden ribbon. And the yellow zone has the maximum number of hours in a year of observational hours. So Epsilon Eridani would get around 1,000 hours of observational time. So you can look at it at different times in the year. But maybe more importantly, it gets up to 150 hours of continuous time. So if Epsilon Eridani is flaring, hopefully you can capture and study that flare. So last November was a really exciting time for Blue Sky Space and the members of the Mauve program as the satellite was launched into a low Earth orbit on SpaceX's Transporter 15 ride-share mission. If I can get my cursor, you can see Mauve on the bottom right-hand corner here with a whole family of other satellites, and Mauve was deployed about an hour after the launch. And since the launch, the operations team have been really busy commissioning the satellite. And I guess the second great piece of news is that we've captured our first spectra. I will say it's very preliminary. It's been captured in the last 24 to 36 hours. So in the coming weeks, we will be calibrating Mauve in readiness for the start of year 1 science operations in the coming months. On that note, I'm going to hand over to Ben.
Thank you very much. So, hello everyone. As Richard said, my name's Benjamin Wilcock. I'm the Senior Science Program Manager here at Blue Sky Space. My role really is to help coordinate the member activities. So over the last year, we've been working with a group of members, currently composed of 20 researchers from the 10 institutions you can see along the bottom of the screen there. And what we've been trying to understand is individually, what are our research interests? And then coming together, because Mauve, as you will know, is a collaborative survey program. So the data is shared with everyone equally. And what we're trying to do is form a cohesive survey. So over this last year, we've been developing those science cases, and we've actually just released our first survey collaboration publication. You can see there on the right-hand side of the screen and the archive code and a QR code if you'd like to access that. But this will go into much more detail about the entire first year of operations, because with Mauve, we do year-to-year planning. So right now we're focused on the next year and the type of science that we want to do. And ultimately, what we've decided as a group is we have 10 core science themes that we'll be undertaking within this first year. And as Richard said, these can broadly be categorized into 4 core areas. So these include stellar variability and activity, exoplanet hosts, hot stars, as well as exotic binaries. So as well as the 3 science themes that you're going to be hearing about today, 2 of which are from the hot stars group and the other one from the stellar variability and activity group, there's a wider set of interests, which we hope to hold later seminars where you can learn more and more about these research cases. Just to give you a kind of a taste of what we'll be doing, it's investigations into M dwarfs, G-type stars in terms of flaring activity and frequency. For the exoplanet hosts, we'll be looking at the impact the star has on exoplanetary habitability conditions, as well as potentially doing some observations for HWO targets to maybe help with future target selection. And then in terms of the exotic binaries that we'll be undertaking, we'll be looking at the different evolutionary pathways for stars in multi-star systems. All of this ultimately means that we've got a really quite diverse range of stars that we want to do. So I wanted to give you a quick glimpse on the next slide at some of the targets that have been submitted for observation. So over the next year, we have approximately 287 targets that have already been submitted. And as Richard said, that field of regard currently on the plot is between around 31 degrees and 47 degrees. In the last few days, we've actually been able to confirm that we're going to be releasing some of the margin that we've been holding on that field of regard. So actually, we'll be able to go to higher and lower elevations in terms of what will be observable. So I would anticipate our members submitting new targets for observation. Maybe this list might change. But what we can see is we've got a really nice distribution in terms of observations throughout the entire year, but also in terms of spectral type. So our targets are ranging from M all the way through to O type stars, predominantly with more of a focus on the brighter stars, as Richard said, given Mauve's size and resolution. We're optimized more for those brighter targets. But what's more important to pay attention to is the location of these targets. So as Richard said, we have this golden ribbon that runs through the center of the field of regard currently, and that's where you're going to have the most observability. And I guess if you're breaking down the science themes into terms of observational strategy, we've got 3 core observational strategies that we'll use. Certain science themes, such as the flaring frequency science themes, have elected to only observe maybe 1 or 2 targets. But what we want here is very long observations. So we'll be doing at least 100 hours on certain targets continuously. And we're very likely to do multiples of these 100-hour long observations because in total we have 5,000 hours for the 10 science themes. In addition to that, then we've also selected to do very short, what we call snapshot observations. And these could be only a few seconds long, all the way through to tens of minutes, depending on the type of star that we're looking at and the information that we need to gather. Obviously, with these, our members typically have very long lists of targets that they'd like to observe throughout the year. And then a slight variation on these snapshot observations would be our repeat snapshots, where, for example, in the exotic binary science theme, we'll be repeating some of these observations. So we may go to 80 or 100 repeats of these observations throughout their observability throughout the year. So all in all, this creates a very vast data set for us where we have these big statistical studies that we'll be working on as the data becomes available, but also these much more focused granular studies on very specific targets. All of this data will be compiled into what we call our Star Drive platform, which is really where we house not only just the data, but all of our collaboration features. So this is a custom platform that's been built by our software team internally for the requirements of our space mission. And the idea with this is it's supposed to be as easy and as simple to use, but the tools are supposed to be very powerful and they're regularly maintained. The reason for this is we're not just working with senior academics. We also have PhD candidates who will be developing and leading many of the science cases that you'll see presented today, but also over the course of the coming seminars that we'll be holding. So not only will you get your data access portal through here, there's the collaboration features where we have publications portals, so everyone knows what investigations are being worked on and what targets, target requests, and then also most importantly, the simulation tools. So we do have a payload simulator and there is a public version of this payload simulator as well. So if you would like access to this, I would suggest reaching out to Richard. You can run up to 400 STIS spectra and run them through the Mauve payload simulator to understand if there are targets of interest you might like to undertake with Mauve. whether the performance is right for the type of research that you're doing. And then I guess I'll stop talking at this stage, and I'm going to move on to the main part of today's presentation, which is really an opportunity for our science team to present the work that they want to do with Mauve over the next year. So I'm going to invite my colleague, Dr. Emma Whelan from Maynooth University in Ireland, to present her science case. And please, whenever you're ready, Emma, take it away.
So so thank you very much, and thank you for the opportunity to talk about the work I plan to do with Mauve. I received research funding from Taiga Éireann or Research Ireland. Okay, so sorry, I'm not sure if you can see my slides, hopefully. I just got a strange message there. But anyway, I received research funding from Research Ireland for the science that I plan to do with Mauve. And I study star and planet formation. And I'm particularly interested in the stage in the formation of a star where planet formation has already started. So I'm interested in whether the processes that are involved in the formation of a star also influence planet formation. And this occurs when the young star, the pre-main sequence star, is about 1 million years old. And so we know that there are different processes at play, which this cartoon here illustrates. So we have accretion, which occurs from the molecular cloud onto the star. And this happens via the accretion disk. Because of angular momentum and the magnetic fields, you get outflows, jets and winds launched as part of this process. And we know at this stage, at about 1 million years old, we have a planet-forming disk with protoplanets forming in it, and we've detected them in a very few cases. So this just is some observations of some young stars. And so in the first image here, you'll see that this is a young low mass star. And what we see here is a full disk. Then we know as the star evolves, we begin to see these gaps in gas and dust in the disk. And we believe that these could be related to planet formation. When we first saw these images, we were certain that there were planets present in these disks, but actually we've only detected them in very few cases. And then the next stage, at about 5 million years old, is where we actually begin to see larger gaps in these disks, and we can actually detect planets. Now, saying that we've only done this in 2 or 3 cases so far, but the technology really is improving, that I believe is going to enable us over the next few years to detect more and more of these protoplanets at these early stages. And then at the million years, tens of millions of years, we actually begin to see planetary systems. So what I'm interested in is how we go from these full disks to these planetary systems, and what role accretion and outflows play in this evolution, you could say. And one thing we know is important, and one thing that I'm also studying apart from the outflow and the accretion is the variability. And we think that the variability can tell us a lot about what's happening in these disks and whether or not planets are present. And this is where Mauve comes in, because this allows me to study young stars with Mauve over a period of a few months, and to get repeat observations. So like Ben mentioned, we're going to do these repeat snapshots to build up light curves of my targets, and to look for variability, and to see if we can connect this variability to the early stages of planet formation in these disks. So typically, to do this work, I would use instruments on the VLT, like UVIS and Muse. So we do high-resolution spectroscopy. I also do a lot of integral field spectroscopy. And these are just some very quick examples of the kind of work that I do. So you can see spectra taken with UVIS of various different emission lines, and images of the outflows, some really beautiful images of the outflows taken with this instrument Muse. And we'll come back to this in a few slides. So as I mentioned, we see this variability in the young stars. So the examples that I've shown you already were low mass stars, so stars of about 1 solar mass. And we actually see a spectrum of variability. So we see these very long period outbursts, for example, which we call FURI outbursts. But we also see bursts and fading with periods of days that typically last for about 10 days. And these were discovered using light curves, so primarily from tests, for example. And they were observed over periods of months, and light curves were made at optical wavelengths. And we saw these bursts, which we believe are related to accretion, but we also see this fading, as I said, which we think is related to early stages of planet formation. So that there's material in the inner disk, which is orbiting the star, and it's causing these periodic dips. So I've shown on the right here a couple of examples of these kind of light curves, and you can see on the one on the bottom, you see these more regular dips. And this, for example, could be caused by orbiting material. And then we see these aperiodic dippers. And this could, we think in some cases, or one theory is that material that could go on to form planetesimals or young stars is being captured by the star, and it's the infall of this material onto the star that causes this dimming of the star. So it's really interesting behavior, and it's really important for us to understand it in order to get a better understanding of what's happening in terms of planet formation at these ages. So as I said, my idea then with Mauve was to look for this behavior in a sample of stars. And with Mauve, we're going to target the Herbig A and B stars. So we already know a lot about variability in young stars for solar mass stars. And as I said, we have lots of light curves from instruments like TESS, but we know very little about this for the Herbig A and B stars. So Herbig A and B stars are intermediate mass young stars. They have masses of about 2 or 3 solar masses and greater. And we know that they have a lot of similarities with low mass stars. We see accretion, very similar accretion, and we see outflows, but we also know that they have very different magnetic fields. We also have some images like the ones I showed at the start for the low mass stars of their disks, where we see these gaps and spirals and evidence of early planet formation. So our idea in Maynooth was to observe a large sample of Herbig stars with Mauve and to look for this behaviour. There has been some study already just in the last couple of years where it suggests that this behaviour might be, they might have a lower incidence of this kind of behaviour, especially of the dipper behaviour in this class of young stars. So maybe just to tell you then a little bit about some of the targets that I plan to observe with Mauve. This is the sample that we've put together so far, and you can see that we have the number of repeats that we've requested and that we hope to get for these objects. And we, at the moment, we expect this to come to about 600 hours of observing time over the first year with Mauve. So really, we would not be able to get this kind of observing time on any other telescope. So this is the strong value of Mauve for us, for the science that we want to do. And then our plan is to follow up on interesting targets with these instruments on the VLT that I pointed out, with Muse and with other VLT instruments. And we hope to be able to do that in the second and third years of our project. And as Richard and Ben have already said, you know, one of the advantages of observing with Mauve is that, or being part of the science programme, is that we can adapt as we get the data, as we have interesting data and we see interesting results for certain targets. Perhaps we can decide to focus more on one target, and we can change our programme in the second and the third year. So this is another big advantage for us. Just quickly to show you some examples of 2 of the objects. So this one, HT 163296, is a really interesting Herbig star. It has a very nice disk. So on the top right, you see this is a Muse image of the jet with an image of the protoplanetary disk of this object taken with ALMA superimposed on it. And so there's lots of evidence for planet formation in this disk. We see that it has these aperiodic dips, so we have some evidence of this already occurring. And so we're really excited to see what the Mauve light curve is going to look like for this object. These are some simulations that we did when planning the observations with Mauve. And so what we have here is some X-shooter spectra shown in the grey. And this is an instrument that's on the VLT. And you can see there's spectra taken in 2011 and 2009. So you can see the variability in this source. And then the red points are the Mauve data points. So the fluxes that we expect to be able to observe with Mauve in about 5 minutes. One important way of actually studying accretion from these young stars is to look at the H-alpha line. So one of my colleagues in the Mauve Science program, Christopher Johns-Krull, is actually going to do a study which is more focused on accretion in Herbig A and B stars. And so this is a spectrum that they produced for one object, ABR, and they compare, I think again, it might be X-shooter spectra with what they expect to see with Mauve. So even though we have this, it's very low resolution, it's still expected that we should be able to extract some information from the H-alpha emission line on the accretion physics. So that will be really interesting for us as well to see what we can get from that. And then just one other object I'll mention, ZCMA. It's another really interesting Herbig A and B star. It's a binary. It has jets and winds. It has evidence of planet formation. And in this case, we do have a light curve already for this object that we can compare to. So we will get another light curve with Mauve, and we can compare it to earlier data. And we're also interested in looking for flaring in this target with Mauve. So with that, I'll finish. I think my 10 minutes is up. And just to say, I'm very excited to see what the Mauve light curves are going to tell us about these young stars. Thank you.
Wonderful. Thank you so much, Emma. If anyone has any questions, I encourage you to pop those into the Q&A button that Richard showed you at the start of the meeting. It's just down along the bottom of the Zoom bar. If you have any questions, please do add them there for Emma. Okay, I'll move us on to our next talk then. And if you do have a question for Emma, we'll have another general Q&A session at the end as well, where you can also ask. But our next talker then, Anusha Ravi Kumar from Western University in Canada. She's going to be talking about the classical BE star survey.
All right. Hi, thank you so much for the kind introduction, Ben. I would also like to mention that our little research team also includes my supervisor, Dr. Aaron Siggett. And our research is also funded by NSERC Canada's Research Discovery Grant. So I'll not make you all wait till the end of the presentation. I'm just going to open this surprise right away. So what do we want to do with Mauve? We are trying to study a group of stars called as classical BE stars. And we would like to understand whether these objects are indeed rapidly rotating or not. Now, in order to address this central question, there are actually 3 components to contextually place them in the perspective of Mauve research. For that, we will address what classical BE stars are first. So these are massive stars of spectral type B. These objects are surrounded by a gaseous equatorial decretion disk. And when you look at these objects spectroscopically, you see prominent emission lines in the spectra. And the most strongest of them all would be the H-alpha Balmer line, where instead of an absorption line, you see a beautiful and strong emission peak. The emission peak is indicative of the gaseous disk surrounding the star. And the classic feature of these type of objects is that the central star is rotating rapidly, and the material from the star is getting ejected outward, and that is what forms the disk. This is exactly opposite to the accretion phenomena that Emma addressed in the talk before. And what is that about critical rotation speeds that is so interesting and that needs to be addressed with Mauve? That is what we see in this graph here. So the x-axis is the spectral type and y-axis is the rotation velocity, the projected speed at which these stars are rotating. The red line that you see here represents the critical velocity of each spectral type. This is the speed, minimum speed required, where the gravitational field balances the centrifugal force and helps material launch. The black color curve that you see at the end are non-rotating normal B-type stars whose rotation velocities have been measured using spectral line widths. And the blue color line you see here represents classical B stars that are rapidly rotating and objects that do have a disk around them. Now, this type of values do clearly show that B stars are indeed rotating faster than normal B-type stars, and that feature does have an important part to play with the disk formation itself. But there is a problem with the physical theory that they are not fast enough to eject material by themselves naturally. So this gap is what about 160 years of research is still chasing behind. And it's also a similar type of question we would like to address using Mauve. So we want to know whether the measured rotation speeds that have been historically addressed for these type of objects is true, or whether there are some inherent bias in observations which we can address through some other techniques independently and check whether there is any discrepancies or observational bias in the measured rotation velocity or not. So this is what we are trying to do with Mauve. Now, think about the rapidly rotating central star. Compared to a normal spherical star that is not rotating as fast, these objects, because they are rotating rapidly, get squished. And this also leads to differences in flux across the surface of the star. This is what we technically call as gravity darkening, where the poles of the star are much brighter compared to the cooler equator of the star. And this effect can be clearly seen in the spectral energy distribution of a star, because the SCDs are typically an average of the temperature and flux distributions across the surface. So the SCD here shows an example of this type of effect and how the flux levels changes when we observationally measure these type of rotational differences in stars. So here, if you should be able to see three different curves. All of these are for spectral type B8 for the temperature of this particular spectral type. The red color dotted curve that you see in the background is the black body curve for that temperature. And the blue color dashed curve you see is for a spherical non-rotating star of the same spectral type. And the black color curve is for a star that is of the same spectral type but rotates at 95% of critical velocity. So the VF represents fractional velocity, meaning how fast the star is rotating with respect to its critical value. Now you can see that compared to a non-rotating star, so there is a wavelength of about 4,000 to 6,000 angstrom, before and after which you see significant changes in flux due to this rapid rotation and flux differences on the surface. So this is what we are trying to cap on to do the measurements of rotation velocity using Mauve. To put this into perspective, what we will indeed do is we will model these type of spectral energy distributions of different spectral types, of central stars having their mass, radius, luminosity, how far they are from Earth, the inclination angle, and how fast the central star is rotating. So all of these values will indeed influence the flux values and indeed the SCDs. For each spectral type, we will develop an array of SCDs changing all of these parameters. And we do indeed try to normalize each of these SCDs for each spectral type at a wavelength of about 6,000 angstroms. And we will try to see the differences in UV flux that is a direct effect of how fast the star is rotating. So with Mauve, once we start having the observations coming in, we will be able to compare the observed data which each of these models that we have developed, and we plan to do it using XSpec, and this will give us an independent way of estimating the rotation speed of these stars without having to rely on the spectroscopic measurements of these objects. Now, how do we plan to do that? We have about 65 targets in total. This includes classical B and A type stars. All of these are rapidly rotating objects compared to their critical velocity. We have selected these objects based on a few criteria, including the field of regard that we discussed earlier, the spectral type, how bright these targets are, whether or not we will be able to measure good signal using Mauve for these targets, and whether we'll be able to detect sound scientific results. And the total exposure time for our science observation will be about 5 hours. It can indeed be expanded as the field of regard changes. We would be able to do repeat observations for certain targets depending upon the science results we get. our results, our sample does also include a few targets that are there for flux calibration, so that we can see whether the effect in the SCD is prominently visible for the targets of our interest or not. That can be regularly checked. I do like to indicate that there are a few modeling complications we have to keep in mind when addressing this science case, one of which would be, since all of these targets are surrounded by a disk, the observed flux will be affected by the disk, and that can be taken into account by our models. And there are also a few targets where the field of observation is indeed contaminated by other brighter targets. But our models do have the capability to include flux contribution from those targets as well, and can be corrected as we go. We also do plan on obtaining near simultaneous H-alpha spectra, and the main reason to do that is to confine the inclination angle of these objects, so that we don't have to change additional parameters to confine the SCD. So this would be the overall plan, and that brings me to the end of my talk. I'm happy to take any questions if there are. Thank you.
Thank you very much, Nisha. Any questions we want to add in the chat there? Parul, have we had anything?
Hi, Ben. Yes, there are a couple of questions, so I'll read them out. So David is asking, well, first of all, very nice talk, Anisha. Isn't there a degeneracy between rotation velocity and inclination? Can you partially lift it with priors on the line profiles?
Yes. So the measured rotation velocity does get affected by the direction in which the rotation axis is oriented in space with respect to the observer. We do plan on confining the inclination angle of the targets of interest by the H-alpha emission profile. So we do have models of emission profiles of classical B stars from the models that we use to develop the SCD. We would be able to use the emission profile, fit that with the model H-alpha profile, and deduct the inclination angle beforehand, and then use that to confine the SCD to deduce the rotation speed. Yes, that's the plan.
Thank you, Anisha. There is one more question by Gerard, and he also comments, great talk. For some of these targets, example Vega, direct imaging from optical interferometry independently confirms their rotation state. Will these be used to baseline the models?
Yes. So if you think about the SCD example that I showed for a non-rotating versus a rapidly rotating star, for each of these models, I do confine the rotation speeds with reference of Vega to make sure that the flux measurements are calibrated and of the right within the right error estimates. And another reason why I do plan on including the interferometric targets is because, as I mentioned, the flux differences on the surface also do affect the measured flux in the SCDs. And because interferometric measurements have confined the rotation speeds and the flux variations across the surface, this would be like an additional parameter that I can use to make sure that my models and their comparison with observed data is indeed within the error estimates, and the range of parameters that I need to vary are confined because of this. That's the plan.
Wonderful. So there's one last question that I'll take for you. It's from Danielle. He asks, how do you model gravity darkening? Do you use the Roche models? Have you tried using the approach described in Lara and Rutord 2012?
At the moment, our models are just using simple Won-Sippels relation, where the black body, the Planck function is dependent upon the gravity effective gravity of the surface, which is a function of temperature, and another power parameter called beta, which you can vary depending upon the spectral type. So this does take into effect the fact that later spectral types, like cooler spectral types, do have prominent and pronounced effects of gravity darkening. And at the moment, our current models rely on this difference, but we are only using Won-Sippels relation at the moment for this.
Great.
Brilliant.
Thank you, Anisha.
Thank you so much. So then moving on to our next talk, Dr. Alejandro Nunes from Columbia University, who's going to be talking about magnetic activity in main sequence low mass stars.
Thank you, Ben. Let me share my slides now. Well, thanks everyone for being here. So the main topic of research, and by that I mean my supervisor Marcelo Guerreros and myself, is related to the question on how can we use indicators of magnetic activity in low mass main sequence stars as age indicators. Because as you may know, once a star reaches its main sequence life, it remains for the most part the same until it becomes a giant. And so it's relatively hard to figure out the age of a random field star. But we know there are some indicators, one of them being magnetic activity, another one being the rotations of stars. And so we've been focusing on understanding how different indicators of magnetic activity evolve over time by looking at stars in open clusters of known ages, and as well as the distribution of rotation periods in stars in open clusters. And this whole enterprise started more than 50 years ago with this seminal paper by Andy Skumanich, in which he showed how for stars in different clusters, their levels of calcium-2 lines, which is the bottom line that you see there, of rotational velocity, the middle line, and of lithium abundance, the top one, are decreasing over time. By the way, he did this with 3 data points, right? So it was Pleiades, Hyades, and then the sun. And that was enough to show, hey, these quantities are decreasing in low mass main sequence stars. And so since then, there's been plenty of studies trying to understand better how this relationship works. And the cool thing about all these indicators is that they're spread out across the stellar spectrum, depending on where they're originating in the atmosphere. Because the point here is that the stellar magnetic field is dumping energy onto the atmosphere of the star at all separate layers. And so the atmosphere then becomes bright, and then we can discern emission coming from the atmospheres. So here's a representation. This is more or less like theoretical work, I guess. For the sun, in the x-axis, you see the distance from the surface, from the photosphere being on the right. And then the y-axis is just the temperature of the plasma in the atmosphere. So the solid curve that you see is basically the temperature of the plasma as you move away from the solar surface. And indicated are different spectral lines that are generated at different heights, right? So I can highlight let's see, the H alpha line, calcium-2 lines, the magnesium-2 lines, also Lyman alpha, etc. And so these are all spread out throughout the optical as well as near UV. If we were to continue up here towards much higher temperatures, million degrees, we reach the corona, and X-rays are produced in the corona. So X-rays will be yet another indicator of magnetic activity, because the way they serve as indicators is that the hotter the plasma is, the more emission comes out. So the more emission we detect in these lines, we're assuming then that the magnetic field itself is stronger, right? Now, there's been several kinds of studies relating magnetic activity with age. So this is just a small example. The top left relates the calcium H and K lines with age. So this is, again, looking at different open clusters. The one on the top right used Galax near UV data to relate it to age. So again, looking at stars in several open clusters. And this particular one, this study was pre-Gaia, and so not a lot of parallaxes known back then. And so they were using this ratio of excess of NUV versus the J near infrared band as a proxy for the strength of that UV emission. And then here at the bottom, I'm just plugging in my own work here with Marcel, we looked at X-rays, both detections and non-detections for stars in several open clusters, try to see how they related to age. And so they're all pretty much showing how all these indicators are decreasing with age. Now, as I mentioned at the beginning, something else that is decreasing with age is the rotational speed of these stars, right? So these stars are losing angular momentum through winds, through the stellar winds. And we're motivated by both things. So one is looking at the decrease in magnetic activity and also the decrease in rotation. And what that's mostly for rotation, it's mostly my colleague, Jason Curtis, who also works with us at Columbia. This is a work from a couple of years ago now, where he finds how for some spectral types, mostly K and M dwarfs, their spin down, their expected spin down stalls. And so what you're seeing here is that the x-axis is just the stellar mass of stars in several separate open clusters. The y-axis is the distribution of rotation periods for the star. So the higher you are in this figure, the more slowly you're rotating. And so what you expect is that stars drift upward in this figure. So from Persepi, which are the green data points here, which is around 600, 700 million years old, you go up to the yellow stars, which are closer to 2.5 giga-year-old stars. And if you were to follow a Skumanich-like relation, you would assume that stars, you would expect stars to follow the solid yellow line. But they don't. The K and M dwarfs stalled their spin down. And so we ask ourselves, do we see this also in activity indicators? So they're physically linked, right? As I mentioned at the beginning, rotation and activity. So this is where we're coming from. So with Mauve, we expect to observe several open clusters. On the left, I'm showing you stuff we've been working on for the 4 open clusters that you see there. They span ages from about 300 to 700 million years. And we're looking at the whole distribution of Loma stars from mid-EVs, more or less, down to M dwarfs. And here, I'm just showing you a simple comparison of NUV fluxes. And so we want to recreate a similar study, start with recreating this study with Mauve data, looking at open clusters or stars that span a broader age range. So starting from AB Doradus, which is 120 million years old, more or less, all the way to a nice sample of field age stars, which we assume to be, giga-years old. And so what we expect is to be able to see the progression of the UV, decreasing UV and optical. Compare those against H-alpha, X-rays, and rotation periods that we already have for most of these stars. And that way we can characterize that UV decrease across the ages. And one important point here is that when we are comparing UV against, let's say, H-alpha or calcium-2 and X-rays, we're determining how that decrease is compares at the different layers of the atmospheres of these stars. I guess there's much to say about what we plan on doing, but this is more or less our first year plan. So I'll just stop there for questions.
Wonderful. Thank you so much. Any questions for Alejandro?
There is one question for Alejandro, for Damian. He asks, will you look for supersaturation?
Thanks, Damian. Yeah, so it would be exciting if we see supersaturation, which is when super fast rotators show a decrease in activity. Because the faster the stars are spinning, you expect higher levels of activity until you reach a saturation level. But for super fast rotators, then that level starts decreasing. And it will be cool to see, except that most of our targets or I should say all of our targets for this first year are going to be F and G dwarfs. And so even at the age of AB Doradus, which is 120 million years old, that's the youngest, these F and G dwarfs, they're already starting to drift towards the unsaturated regime, right? So where they've spun down enough that now there's a polar relationship between rotation and activity. So maybe in the future, when we try to observe some M and K dwarfs at young ages, we may be able to see supersaturation.
Wonderful. Thank you very much. And Richard, we'll hand back over to you to wrap things up for us.
Great. Thank you, Emma, Anusha, and Alejandro. Some really interesting talks there. So I'm aware that it's only 2 minutes to the top of the hour, so I will move quickly through the next couple of slides. So a quick note about year 2. So today's talk is a session very much focused on year 1, and I hope you've got a greater understanding of what we're planning to do as part of that program. We will open and start the planning for year 2 of the science program in April 2026. And then year 2 science operations will begin in 2027. Just as a reminder, we plan the survey program on a year-by-year basis. So that's a great opportunity to get involved, to join. We can either extend existing themes. Many of our members have joined for multiple years already. But I think it's a great opportunity to develop new ones. We will have the true in-orbit performance of Mauve to share. Our tools will be updated so you can get a good flavor of the performance that Mauve can give you and ultimately the science that you can do. So if you are interested, please contact me. There's my email address there, richard@bssl.space. I think Ben mentioned this earlier. Here's a QR code if you want to try the payload simulator. We will let everybody know when we update this with the true in-orbit performance, but I assume this will be many months until we've characterized that and updated the software. But it is working now with the pre-launch software and algorithms. So that leads me on to the next webinar, which we will be holding, and this will focus on the commissioning process and first light, where we will describe the initial results and science performance we are getting from the Mauve satellite before science operations begin. If there are no questions, I'd like to thank all of our speakers today, Emma, Anusha, Alejandro, for giving such interesting talks, and also thanks to Marcel and Ben for supporting the webinar. And finally, thank you to you for taking the time to join us. Hopefully you learned something about Mauve and the first year of the science program. As a reminder, if you do want to discuss how Mauve could help your research, then please feel free to contact me or one of the team, and I can set up a call to explore options. And on that note, I'll close today's session and hope to see you at the next webinar.